All right, so in 9.4, instead of talking about central angles and how they're related to arcs, we're going to talk about how the arc is related to the chords that are in circles. And there are a few theorems that are in this lesson. First one is that congruent arcs have congruent chords, and congruent chords have congruent arcs. So as long as we have the same circle or congruent circles, the arc that's formed by the chord's endpoints, as long as it's congruent to the other chord from the congruent circle or the same circle, then the arcs that are highlighted would be congruent as well. They would have the same measurement and they would have the same angle measurement. The next theorem says that if a diameter that is perpendicular to a chord bisects the chord at its arc. So taking a diameter and making it perpendicular to any chord, not only does it bisect the arc, but it also bisects the chord, and we're going to see some more examples of how this can play a part in us finding some missing sides and some missing chords. Last theorem. Chords that are equally distant from the center or centers of congruent circles are congruent, and congruent chords are equally distant from the centers. So therefore, we could start stating that as long as we know that the chords are congruent, we could say that the segments that connect the center to the chord is also congruent to the other segment, and that wouldn't be known as a radius or anything like that. As you can start to see, we would be able to apply a lot of things here, because the only thing about these two dotted lines is that to find the distance from a point to a line, you have to find the distance as a segment perpendicular to the chord. So everything that we're going to be talking about from the distance from a point to a line has to do with these two dotted lines being perpendicular. As you can see, this also allows for us to take another line and draw a radius from the center point to the end point of the chord, creating a right triangle with these three segments. Hit pause now and answer questions 1 through 4 on your worksheet. Okay, a couple of those examples that were previously mentioned are shown here, where we're trying to find the missing side length x as it relates to the chord or the segment. And as you can see, we have a 90-degree angle and then some right triangles that are involved. Hit pause and answer questions 5 and 6, finding the side length x. In number 5, the 4.5 means this segment from the chord to the circle, and 4.2 represents the segment from the chord to the edge of the circle. Hit pause and answer these questions now. Knowing that the chord's segment is 9.7 on this side, you can also state that it's 9.7 on this side. We also know that the whole diameter is 25.2, making the radius half of that. After we do that, we can use the 9.7 on this side as well as half of 25.2 to create the Pythagorean theorem and find that x equals 8.1. Same thing over here, 7.8 is our chord on the other side, as well as the 18.8 diameter. Using the Pythagorean theorem, you should find that x equals 5.2. You'll see a bunch of these examples on the back side of your worksheet, and other than the fact that we have those triangles are involved, these are basically the major points of the lesson. So finish the back side of the worksheet, bring it into class, and if you have any questions, we will answer them then.